Okay, so hello everyone. Welcome to the second set of lectures of the Basics of Quantum Gravity School. This school is organized by the International Society for Quantum Gravity, or ISQG in short, and by the ISQG Young Researchers team. Today, in the course of the next weeks, Haggard is going to introduce the fundamentals of loop quantum gravity and spin-foam models. Hal is a professor at the Bard College in New York. He received his PhD at the University of California, Berkeley, and has held positions as a lecturer at the physics department of the University of California, as well as a postdoctoral fellowship at the Center for Theoretical Physics in Marseille. His research interests range widely from gravity to quantum mechanics and their indefinite relation. In particular, questions such as the discreteness of space, the emergence of a smooth continuum. Hal is an expert on quantum geometry and on black holes in the context of loop quantum gravity. And besides that, he enjoys mapping exoplanets. He's an experienced lecturer, and we're delighted to have him giving a lecture in the School of Basics of Quantum Gravity. Hal will take a break at the mid of the lecture to take questions, but also we'll have plenty of time for discussion and questions at the end of the lecture. So that being said, thank you, Hal, for agreeing to participate in this event, and we are very much looking forward to your lectures.
Wonderful. Thank you all for being here and welcome, and a very warm and particular thank you to the Young Researchers Group for this invitation. I'm delighted to be here and discussing these topics. I'm going to jump right in and give you a sort of prologue. I want you to be able to know what I'm like. And so I'm just going to jump in, but I'll give you an overview of today's discussion in just a moment. So my prologue, as Johanna mentioned, I teach at a college where I largely teach undergraduates. And my prologue involves thinking about the gravitational field. And when I was an undergraduate, I remember when I first learned free body diagrams and Newtonian mechanics, and I was often confused whether I had kept track of all of the forces that are necessary for a free body diagram. And when I first arrived at Bard, I had a senior colleague here, Matthew Deedy, who taught me a wonderful trick for teaching this that I'd never seen before, which is to check if you've got all the forces in the free body diagram, you check for all the contacts. So if you look at the skateboarder in this picture, this is from Thrasher magazine, well, in the left part of the picture, when he's on the ground, you just look at all the things that are contacting him. And there's, of course, the skateboard that's contacting him. And so the skateboard exerts a force on the man. But after you've taken into account all the forces of contact, you still have to take into account two more forces, gravity and electricity and magnetism. And for us, the particularly interesting one is gravity. And the more I thought about this, the more it helped me to understand how strange gravity is, right? You can exert a force without contact. You're not touching this person at all, but you're exerting a force on them. And actually that strikes me and many as the weirdest facet of gravity, that force is forces of contact. I can't just wave my hands at you all and move you. It would be absurd. And so the question becomes, why is this? Why is it that gravity can exert this force? In fact, this goes all the way back into the history of the invention of gravity. And this is one of my favorite quotes in the history of science. This is from Newton, and I'll just read it out for you all. That one body may act upon another at a distance through a vacuum without the mediation of anything else, by and through which their action and force may be conveyed from one to another, is to me so great an absurdity that I believe no man who has in philosophic matters a competent faculty of thinking could ever fall into it. I love this quote because Newton is mocking himself, right? He's the person that has come up with this proposal that Newtonian gravity is this force that acts between two bodies that are separated, and he's just saying this is absurd. Well, you all know the resolution of this puzzle. this is what Einstein turned to addressing, was how do we make gravity local? How do we make it a force of contact? And the solution, of course, is to make space-time curved, right? So we often draw this Eddington picture of this curvature of space-time. So we think of space-time itself as a sort of rubber sheet, and you put masses on that rubber sheet and it bends the sheet. And the force of gravity is due to that change in the space-time geometry. And of course, this is the key element of study in gravity, right? Making space-time into a physical entity, into a thing that you can actually think about, means that we can talk about the gravitational field as a physical thing. It's not just an empty space in which masses sit. Now, you all have studied gravity a lot, and I'm going to slowly build up to much more technical discussion. But you know that there are many flaws in this Eddington picture, especially as we draw it here. We draw it this way because it makes curvature most easily visible, right? That the curvature that I can picture is a curvature of 2D surfaces. It's harder for me to picture 3D curvature. And it's certainly hard for me to picture four-dimensional space-time curvature. So we draw this, but it's tricky. And one of the ways in which this Eddington picture fails worst is that it's purely showing us the spatial curvature. So it captures many things accurately by doing that. So for example, if you look at one of these grid boxes near the Earth, you see that the grid box has changed away from being sort of a Euclidean grid box, right? Instead of one of these, which looks fairly square and regular, you see that things are kind of coming together, and the curvature is having an influence. But it's purely spatial. And so the first thing that we have to do to think about this more carefully is to think in space-time, of course. And so here I'll just draw a single spatial direction and the time direction that goes with it. Oh, I'm so sorry, just a moment. I'll even unplug that. So I've just drawn a few simple world lines here. At the far left in orange is a world line of an object that's just sitting still. And of course, it just moves in time. It doesn't move in space at all. The pink world line shows an object that's moving at a constant speed. And the green world line shows an object oscillating back and forth. In all of the examples to the left of the dashed line, I'm imagining that there's no gravitational forces, but perhaps there's some external force on the object. For the green line, you would need some Hooke's law type oscillatory force. But now let's add gravity into the picture. And the wonderful thing is that gravity takes initially parallel objects, initially two objects that are sitting at rest and that are doing nothing, and it allows them to come closer together. And it does that in time. You see, this is the same sort of modification of our intuition of Euclidean geometry, but now it's due to the gravitational effects. So on the right here, we have no other external forces on these two yellow lines. They're just at rest, freely falling, right? But nonetheless, they come closer together. Of course, to really say that they come closer together, we would need to compute the space-time separation or the spatial separation. But you can see that also in this coordinate frame that I'm using here, they pick up velocity. That makes sense, right? We know that objects that are subject to gravitation start moving, moving relative to one another. And that's the key here, is that we see that these two objects are influenced by the gravity in their relative separation. So what can we infer on the right part of the diagram? We can infer that something is gravitating. And so one way that you could get the situation that I am depicting here would be to have a massive body, here I've drawn it in red, that is causing this space-time curvature. And again, the reason that I wanted to emphasize this is that quantitatively speaking, for objects that are not moving at relativistic speeds, it's this space-time curvature that's more important than the spatial curvature. It turns out for photons and relativistically moving objects, the two effects, the spatial curvature and the space-time curvature, equally contribute. We know this, for example, in the famous bending of starlight. You can get both contributions equal. But for objects that are moving non-relativistically, for example, objects that are released from rest, it's the space-time curvature that is the dominant one by far. So I said I was trying to introduce you to myself a little. It's this kind of subtlety that I love in physics, and this kind of aspect of thinking about things carefully and pulling them apart that I find most interesting. For me, this began when I was an undergraduate. The Einstein train argument that simultaneity is relative just completely blew my mind. And for me, my first love in the area of quantum gravity, in the area of general relativity or special relativity in this case, was this notion that time is much more subtle than we first appreciate. And so I am in trying to answer for you my personal answer to the question, why quantum gravity? And for me personally, I'm very excited to understand what quantum gravity is going to teach us about time. I think all the same sorts of remarkable things that we've learned about time from classical general relativity, we're going to have to revolutionize all of those again and learn new things about time from quantum gravity. So for me, that's the first motivator, the first idea behind my interest in quantum gravity. So that's my prologue. The reason for that prologue is that the organizers asked me to begin this series of lectures with the question, why quantum gravity? The personal is the personal. As I said, I do it partly to introduce you to me, and you may not share those interests, but I'm going to try to give you a list, a rather long list actually, of reasons that people think gravity needs to be quantized. And today that's going to be the dominant subject. After that, I want to tell you some of the reasons that I think quantum gravity is hard. Uh, we've been working on quantizing the gravitational field for, well, since the 1930s, if you think of Bronstein. So that's now 70 plus 20, 90 years we've been trying to quantize the gravitational field, and it's still an open problem at the level of people really having a unanimous, agreed upon theory of quantum gravity. So that means it's hard. And we need to understand what some of the reasons for that difficulty are. So the second part of the discussion will be about that. My lectures are going to focus on the approach that we call loop quantum gravity. Loop quantum gravity comes in two flavors: a canonical theory where you make a space-time split and try to understand the theory as a Hamiltonian theory, and in spin foam, which is a discrete geometry path integral. I'm going to try to introduce you to both of these different approaches, but today I'm just going to give you a very, very brief introduction to a few features of loop gravity. Those are going to be motivated by the things that are difficult about quantum gravity. So I'm going to try to show you why I think this is an interesting theory to try and to look at. And then I'll give you a brief overview of the rest of the course. There's 4 more lectures in the course, and so I'll just outline what those are going to be about so you can dip into the one that you're most interested in. As I said, the balance of today's discussion is on these first 2 topics. Part 3 and part 4 will both be very brief and come at the end. All right, so let's get started with the question, why quantum gravity? So the first reason is black holes. And black holes are fascinating objects. And in particular, we have an interesting, timely thing that's happened here, in the last few years, which is that Roger Penrose was awarded half of the Nobel Prize in 2020 for the discovery that black hole formation is a robust prediction of general relativity. So on the left is Roger at the stage of receiving the Nobel Prize. On the bottom right is a picture. I wanted to find a picture. He did this work in the 1960s, and I wanted to find a picture for you of what he looked like in the 1960s. I didn't manage that, but for me, it was almost as much fun to find a picture from 1978 when he was in Berkeley, because as Johanna mentioned, I did my PhD work there, and I actually think I recognized the background of this picture. So this is partly to show you that he was a young person when he did this, and to encourage you that you're perfectly able to contribute quite remarkable things to our theoretical work. So what is it that Roger did? In 1939, Oppenheimer and Schneider realized that if you took a perfectly spherical distribution of matter and you let it gravitationally collapse, that it would form a singularity. So basically, if there's no pressure forces that are holding this gravitational distribution of matter up, it will just continue to crunch down. And what they did actually was look at the density of matter. And this, as you go to the center of the collapsing matter, this goes to infinity. So that's what they meant by a singularity. So in this whole section of the talk, I've stolen hand-drawn illustrations by Roger Penrose. He's a remarkable illustrator. So on the right here, you see a lower dimensional model of this collapse. So you see at the bottom of the figure is the collapsing matter, the spherical distribution of matter getting denser and denser. At some point, a horizon forms, and we'll talk more about what kind of horizon. It's called a trapping surface. And the matter continues to collapse even once it goes within that trapping surface. And eventually a singularity forms. So this is where the density has become infinite. So this has led to this famous phrase that everyone mentions in this context, that general relativity predicts its own demise. No physicist that I know believes that this infinity is really there, that infinite density is a physical prediction of the theory. Instead, what we think is that it represents a breakdown in the validity of general relativity. So general relativity isn't a true theory any longer once we get to this central singularity. And this is one of our motivators for quantum gravity. But I'd like to describe in a little bit more detail what Penrose actually did here. So after this Oppenheimer-Schneider result, researchers started to ask if the assumption on the spherical symmetry that they made was relaxed, maybe singularities are avoided. Maybe gravitational collapse doesn't generically lead to singularity. And here again is a beautiful Penrose illustration. If you started out with a complicated distribution of matter with no intrinsic symmetry, maybe that distribution of matter clumps in a complicated way that comes back out and you never form a central singularity. So that question was on people's minds, and Penrose came up with a way of addressing that question. And it's very much tied with this introduction that I gave. It's tied to the notion of space-time curvature. So just as the gravitation was causing initially resting objects with a given separation to come to change their separation over time, it also changes the causal structure of the underlying spacetime. So here you can see that illustrated by these light cones. And so Penrose's idea was to try to study and understand what it is that becomes of this light cone structure. In particular, he introduced this notion of a trapping surface. So many graduate courses in GR do introduce this, but many don't. And so I wanted to cover this briefly just so you have an idea of it. And again, today I'm staying more at the intuitive level. Don't worry, I'll get much more technical as we go. So consider a two-dimensional surface element. So here it's a little circular disk. And imagine embedding little light sources throughout that two-dimensional surface and allow those light bulbs to emit light. Of course, they'll emit light in two different directions. They'll emit light away to the right in the diagram. Of course, that's going to evolve both in space and in time. So this is a space-time diagram again with the null normal in this direction. But they also will emit light in the other direction. And so any one of them, of course, makes the standard light cone. But we're going to be asking about the full set of all light bulbs. And that's what starts to become interesting. If the sheet, so this initial two-dimensional surface that we're thinking of lighting up, if that sheet is curved and not straight, then the light that's emitted in different directions will have different behavior. So you could imagine a little part of a sphere that you put light bulbs all around, and imagine the light sheet that comes off of that. And the light sheet that moves radially outward from the sphere will grow in area as you move away. But the light sheet that's moving towards the interior of the sphere, of course, decreases in area. You could imagine a spherical light front that's getting smaller and smaller as you go in. So this is generic, that when you have this curved surface, you have these different behaviors in different directions. But a trapping surface is a particularly interesting kind of surface. It's a surface that has contracting light rays in both directions. So here's a schematic depiction. Again, we can't picture the four-dimensional space-time, so this schematic is cutting out one of the dimensions, and it's kind of disappointing in doing that, but it's useful anyway. The idea is that if you take this surface here, and you look at the light rays that leave it to the left, they focus towards P. But the light rays that leave it to the right also focus, they focus towards Q. And so the area of both light surfaces is actually contracting. So this is what we call a trapped surface. It's a very special kind of surface. And it's the curvature of space-time that allows this kind of thing to happen. So if we go back to that diagram I put on the first picture of the collapsing matter, you can see that Penrose has actually done this carefully. You see the first feature that I introduced you to, the fact that these space-time curvature leads initially parallel geodesics to curve towards each other. It's a non-Euclidean geometry. But along with that curving, the light cones begin to tip. And once we arrive at a trapping surface, the ingoing light ray, which is like the left part of this light cone here, is certainly ingoing, but the outgoing light ray is also trapped. It's stuck on the edge of this surface, and that's what makes this surface trapping. As you go even just a little bit further in, both the ingoing and outgoing light rays head towards smaller separations. In other words, both of them focus. So this trapping surface is the key to the singularity theorem. It's what Penrose understood, and it's what he used to then prove the singularity theorem. In particular, under very weak assumptions, collapsing matter generically leads to compact trapping surfaces. So to a surface that's compact in space-time that is trapping. And geodesics within these trapped regions are eventually inextendable. So inextendable is not one-to-one correspondence with a singularity, but it's a strong indicator. And you only have to make weak assumptions beyond that to get to a singularity. But technically what he proved is that space-time is inextendable once you have these compact trapping surfaces. So what were the assumptions? Just to make it a little bit more precise, the first assumption is that the Einstein equations hold. The second assumption is that the matter distribution satisfies some sort of reasonable energy condition. So we'll talk more about how to make sense of this energy condition in next lecture. But for now, just think of it as making sure that the energy carried by light rays is positive for any observer. So this is a very reasonable assumption. And the space-time away from the collapsing matter is spatially unbounded. So you can think of this as a black hole or collapsing distribution of matter in an asymptotically flat space-time. And with those assumptions, Penrose shows that the space-time is inextendable. So this is the result that won the Nobel Prize. And it's quite a beautiful result. In particular, what it gives us today is this, I'll come back to this in just a second, but it gives us this conclusion that we were mentioning at the outset, that singularities are unavoidable in this sense. If you have reasonable matter in a reasonable setting, you're going to get singularities. And if you believe that those really shouldn't be a prediction of GR, but just a limitation in the validity of the theory, then singularities need to be addressed by, for example, a quantum theory of gravity. The other piece of history I just thought I'd mention here because it's interesting is that Hawking expanded on Penrose's work. Penrose's work was in the 1964, Hawking in 66, as part of his PhD actually, showed that you can also apply this to cosmologies. So here you have to take a slightly different energy assumption. It's called the weak energy condition. But if you do that and you follow matter backwards in time, that's the other interesting facet of the theorem. You go backwards this time, you generically, no matter what kind of spatial curvature, arrive at an initial singularity. So these Penrose-Hawking theorems, as they're known, lead to this picture on the right here, which is my final of Penrose's pictures that I enjoy so much, with an initial singularity and black hole singularities forming throughout your cosmology. And so if you want to understand both cosmology in the early universe, going before the cosmic microwave background, before the surface of last scattering, and understanding what's happening at the earliest moments of the universe. If you want to understand that, and if you want to understand how generic matter gravitationally collapses, we're going to have to address singularities. So this is the first reason for a quantum theory of gravity. All right. Second reason, I'm going to give you 5 in total. So my second reason for quantum gravity is that gravity chops Hilbert space down to size. This is been known for quite some time, but this quote I've written here as a quote is from Sean Carroll, who gave a nice online lecture that you can look up as part of the Quantum Information Structure of Space-Time series just a few weeks ago. I like this way of saying it, chops Hilbert space down to size. What do we mean? In quantum field theory, the dimension of the Hilbert space is infinite. This is because each mode of the field is an oscillator, and we can put as many quanta as we want into those modes. Now, I'm not saying that that's reasonable physically. I'm saying that there's nothing in the theory that blocks you from doing that. So in quantum field theory, you just keep adding quanta to any given mode, and there's no reason you can't do it. And this arrives at an infinite energy. But we've just seen that as you get to large energy densities, you encounter a gravitational cutoff to this phenomena. That is, those large energy densities are going to collapse gravitationally. So you put too much energy in a region and you form a black hole. And so that's actually quite intriguing because we have strong methods for estimating the dimension of the Hilbert space of a black hole. The dimension of the Hilbert space of the black hole, well, it's essentially just the number of states you can access. And the number of states you can access is given by the entropy or the exponential of the entropy. And the entropy is the one thing in black hole physics that we really, no matter what approach you take, we seem to always arrive at the same answer. And that's the boundary area of the black hole divided by the Planck area. It's a large number, but it's finite. And so this means that your Hilbert space is not infinite dimensional. This is not said often enough, in my opinion, because it means something quite profound. It means that quantum gravity is not a quantum field theory, not in the standard sense. Quantum gravity has to be more than a quantum field theory, because you can't do this thing of just putting quanta in the same mode over and over and over again. You have to have something that back reacts and changes that and stops you from adding more. So of course you can make a bigger black hole, that's fine, but that's going to change the system that you're talking about. So here I've introduced for the first time the Planck area. This is going to be cropping up again and again. And I just wanted to give you an estimate for the size of this thing to show you how crazy quantum gravity is. So the Planck area is 10 to the negative 70 square meters. So this is really quite astronomical, but conceptually it's extremely important. It's telling us that quantum gravity is not a quantum field theory. All right. I mentioned very briefly a moment ago that there was somebody who worked on quantum gravity in the 1930s. This was following up on Bohr and Rosenfeld's work on the electric field, and this person was Matvei Petrovich Bronstein. And Bronstein was another young researcher and really had insightful and interesting things to say about quantum gravity. So unusually, I'm quoting rather lengthily here. So here, Bronstein says, we should take into account a circumstance that reveals the fundamental distinction between quantum electrodynamics and quantum theory of the gravitational field. Formal quantum electrodynamics that ignores the structure of the elementary charge does not, in principle, limit the density of charge density rho. When it is large enough, we can measure the electric field's components with arbitrary precision. In nature, there are probably limits to the density of electric charge, but formal quantum electrodynamics does not take these into account. You hear the analogy with what I was just saying. There's nothing in quantum electrodynamics that stops how much charge. The quantum theory of gravitation represents quite different case. It has to take into account the fact that the gravitational radius of the test body, kappa rho v, here rho is energy density, not charge density, it's mass density, the charge of gravity, must be less than its linear dimensions, v to the 1/3. So this sounds a little mysterious. By kappa here, I wanted to make sure you knew that he's talking about 8 pi g over c to the 4th. And I want to give you, there's many versions of this argument, but I want to give you a rather simple one just so you have a flavor of what Bronstein is talking about here. So what I'm going to do is a version that's like Heisenberg's microscope. I don't know if you ever thought about Heisenberg's microscope, but it's a thought experiment that tries to explain the Heisenberg uncertainty principle. So Heisenberg suggests the following. Imagine that we're trying to measure the position and momentum of an electron, and we're going to use light as a probe. So I've very schematically drawn it at the right here. We send in a light signal to try and measure the position and momentum of this electron. We measure it with some kind of microscope. So what Heisenberg noticed was that you can resolve the position of the electron more effectively if you use shorter wavelength, just the standard resolution issue of optics. So the uncertainty in your position should go something like the wavelength. And here we could add lots of more careful factors and things like that, but we're just looking for an estimate. Meanwhile, de Broglie has suggested that the momentum of the photon is going like the Planck constant over the wavelength. And so when we send in this photon to try and probe the position, well, of course, we transfer momentum to the electron. And so we disturb its momentum by about h bar over lambda. And so what Heisenberg noticed about this joint measurement of position and momentum is that when you take the product of these two things, it has to be greater than or equal to h bar. So this is the idea of the Heisenberg microscope. But one way of framing what Bronstein was talking about is to just say, okay, I don't care about momentum. I want to do the best position measurement I can do of the electron. I just give up on trying to understand what its momentum is when I take this measurement. Well, in that case, it's clear what you should do. You should go to higher and higher energy photons. You should make this wavelength shorter and shorter such that you're getting better and better resolution on the position of the electron. But when we take gravity into account, we realize there's a limitation on this. That high energy photon is going to start to gravitate. It has energy, and all forms of energy gravitate. So as we make this wavelength shorter, we're making it more massive in essence, that is more energetic. And that high energy photon is going to start to gravitationally disturb the electron. Now you can do the calculation in Newtonian gravity as an estimate, or you can try to think about this from general relativity. But in essence, all I'm looking for here is a dimensional analysis argument. And the dimensional analysis is pretty easy. We take the Planck area that I just introduced you to, h bar g over c cubed, that's the Planck area, and we compare it with the length scale that the momentum is determining. Delta p over h bar is roughly lambda. So we're getting a length scale here. And this is what we expect the gravitational disturbance of this photon we're sending in is going to be. So we see a weird trade-off that happens. If I want to localize the electron better due to optical limitations, I need to use higher momentum, higher energy photons to do it. But the higher I make the momentum, the worse the gravitational attraction becomes. And so the uncertainty in position I get is whichever one of these is maximal. Whichever one's maximal is dominating the measurement. So, you can look for the place where these two cross over. And it turns out, simply enough, they cross over when these two contributions are equal. So the best I can do in localizing this electron is by finding the place where these two contributions are equal, the resolution contribution and the gravitational contribution. So you just do that calculation. It's a simple calculation. You set these equal, you get the delta p squared over h squared. So the length scale squared is the Planck area. So how well can we localize things? Well, because of gravitational effects, we can't localize things better than the Planck area. Schematically, sometimes the way people say this is that if you send in too much energy, you're going to collapse the system to a black hole, and that black hole is going to be the best you can do in terms of measuring the position of the object. So this is a version of the Bronstein argument. Bronstein does something slightly more sophisticated. He looks at the field and the Christoffel symbols and asks how well you can measure those components. But this is where his conclusion comes from. The elimination of the logical inconsistencies connected with this result requires a radical reconstruction of the theory, and in particular, the rejection of a Riemannian geometry dealing, as we have seen here, with values unobservable in principle, and perhaps also rejection of our ordinary concepts of space and time, modifying them by some much deeper and non-evident concepts. I love this quote. I mean, 1936, and he's saying, whoa, we have a fundamental length scale here, a fundamental scale on which Einsteinian gravity has to break down. So this is my third reason for you that, that we need a quantum theory of gravity. There's no good localization. It's quite similar to the second one, right? Gravity can't be a quantum field theory. That means we can't do localization down to arbitrary scales. All right, fourth reason. Moving along at a good clip here. I hope it's all right. Matter is my fourth reason why we need to quantize the gravitational field. Matter is, of course, quantum particles. So matter sources the right-hand side of the Einstein equations. I've written it out here. But matter is quantum mechanical. And so we know that this object summarizing the matter contribution on the right-hand side of the equation, this object has to be quantum mechanical. In Wheeler's famous words, uh, gravity tells matter how to move, and matter tells gravity how to curve, or space-time how to curve. But if we quantize half the equation, what are we going to do with the other half of the equation? We can't just stick an operator in here and be happy. That's a completely contradictory equation. So there's a long-standing approach, which is to study quantum field theory on curved spacetimes. So we can do this in a couple of different ways, all of which are pursued. Classic textbook on this is Birrell and Davies, or Wald has a beautiful textbook on this as well. So we study the quantum field in a curved background. Or another approach is to replace the operator stress energy tensor by its expectation value. So then we actually are studying a consistent classical theory on both sides. Sometimes this latter approach is called semi-classical gravity. I'm never going to refer to it that way. I want to warn you that because the literature refers to it that way quite often. I think it's a really bad misnomer. There's a whole field of semi-classical physics in which you try to understand the small h bar limit of quantum theories. And that small h bar limit is quite distinct from doing something like this of plugging in expectation values. So I'll always refer to this set of techniques as quantum field theory on curved spacetimes. I think it's a much better way of thinking about what people are doing here. QFT on curved spacetimes is tricky mathematically. One of the things you encounter almost immediately is that you need to renormalize the stress energy tensor to make sense of the theory at all. And that also requires that you have careful consideration of your choice of states. So matter is immediately telling us that something special has to happen. Some kind of quantum theory of gravity is necessary here. Just a few more comments on this, because I think you can get a pretty nice, accessible way of thinking about this. In Fock space, so in the space of standard quantum field theory, there's a symmetric vacuum that we use to understand the theory. It's completely Poincare invariant. I can make translations, I can make boosts, rotations, and always with that vacuum state has 0 particles. All inertial observers agree on the particle content of this vacuum, and it means that we know what we're talking about when you and I are moving in different ways, different inertial ways, and we can agree on, well, there's no particles in our vacuum. This completely changes for non-inertial changes of frame. If you're in an inertial frame and I start accelerating with respect to you, and you say, I observe the vacuum state, I'll report that there is no vacuum, that there's particles all over the place. In fact, it turns out that what I report is a thermal state. So this was established in a series of works in many different contexts. So Parker very early on worked on this in his PhD thesis in the context of cosmology, that cosmological evolution can lead to particle creation. The most famous example, the one that you've almost certainly heard of, is Hawking radiation from a black hole. But even in the simplest context I was just mentioning, where you just go to a non-inertial frame, Unruh and Davies and Fulling each independently found this effect. So in the context of accelerated observers, we often call this a Rindler spacetime. And you can find the so-called Unruh temperature of the thermal bath of particles that you see. Let me focus on the black hole case because I think it's probably the one you're most familiar with. In that case, what Hawking found was that that you can associate a thermal state to a black hole when you sit outside the black hole as a stationary observer. So in essence, this connects the acceleration and the black hole case. If we're not just free falling into the black hole, but we're staying stationary stationary at some radius away from the black hole, we're accelerated with respect to the natural gravitational field. And that's a way of understanding why we see a thermal state. And the Hawking temperature, well, today I've included constants everywhere, and in the future I'll set many of them equal to 1, but I wanted you to see how the units are connecting with each other for today. So here's the Hawking temperature in all its glory, but the main dependence is this 1/mass dependence. So smaller black holes radiate at a higher temperature. In particular, to give you a sense of the scale, it turns out it's 10 to the -8 Kelvin per solar mass. So if you had a solar mass black hole, then we would have 10 to the -8 Kelvin radiation coming off of that black hole. Well, unfortunately, here again, you see this thing that the scales of quantum gravity are totally nuts. So this is well below the cosmic microwave background. So if you have a solar mass black hole, of course, there's no way we can see its radiation. It's absorbing particles from the CMB. Even in empty outer space, that black hole is not going to be showing off its Hawking temperature. But one of the things that's changed a lot in the last 5 years, I think you all are doing well to come to the field now, is the measurement of gravitational waves and the discovery that black holes are much more varied and much more interesting than we understood before. In particular, it's reawakened interest in the question of whether there are primordial black holes that were formed in the very early universe that don't have to form necessarily by the standard gravitational collapse mechanism, right? In standard gravitational collapse, you have a hot star. That star runs out of its nuclear fuel, and then it has a runaway process where the gravitational forces take over and collapse. But if somehow a black hole was formed in the early universe, it's possible that it could be formed with a different kind of mass spectrum. In particular, you might be able to form black holes that are much lighter than the standard black holes we see in our astrophysical environment. And if you were able to sort of form asteroid-sized black holes of masses much smaller than the sun, you could start to get appreciable Hawking radiation. So all of this fits together in this need for a quantum theory of gravity in order to make the Einstein equations consistent. We can't put quantum matter on one side of the equation and just leave the gravitational field alone on the other side of the equation. My fifth and final reason for today is that is a consequence of this Hawking evaporation. So the Hawking temperature means that black holes can radiate, which means if we could isolate them well enough, or if we could make a small enough black hole, that we would expect it to completely radiate away. And the question becomes, what do we make of this central singularity? What do we make of the interior of the space, black hole space-time as this evaporation proceeds? Again, the scales are quite astronomical. So if you took a solar mass black hole, the central figure gives, well, suppose it only radiated via Hawking radiation, then it gives a lifetime for the black hole that scales as the mass cubed. Again, this isn't really reasonable. We would expect that as this black hole gets smaller and smaller, there are nonlinear effects that kick in, and there's a back reaction between the radiation and the black hole that changes this timescale. But this timescale is just an estimate. It's an estimate based on imagining that the Hawking evaporation proceeds the same way for all times. Then you get 10 to the 67 years for a solar mass black hole. This is one of my favorite numbers in the field. The age of the universe is around 14 billion years, so that's 10 to the 10th years. This is 57 orders of magnitude larger than the age of the universe. If this is really how black holes evaporate, if this is really the life cycle of a black hole, then it's a different scale than any other scale I know in physics. So the question is, should we really believe a Penrose diagram like this one on the left? Collapsing matter forms a black hole. This is the black hole horizon and a central singularity. And this is drawn quite often, actually, conferences and regularly people sort of seem to say, well, after it evaporates, you just have standard space-time after that. It's quite hard to believe, actually. If you dig into this Penrose diagram and start thinking about what must be true at the edge of this diagram, it's quite hard to make sense of what is being said about the causal structure of the space-time here. Within loop gravity, a proposal is that it's a trapping horizon that forms, not an eternal event horizon. That trapping horizon allows for the Hawking radiation, and that somehow there's a region of space-time, this central shaded region, where we really need quantum gravity. The central singularity is resolved by the quantum gravity, and it allows for a reasonable evolution of this whole space-time more globally. That after the evaporation of the black hole, you can see what's going on the other side of this space-time. So my fifth reason is that if black holes evaporate, we need to understand what happens at the end of their evaporation. We need to understand whether the central singularity is exposed. We need to understand what it is about quantum gravity that makes sense of this evaporation process. All right, those are my 5 reasons why quantum gravity. I'm about at the halfway mark. I'm going to stop and see if there are questions. If there are no questions, that's totally fine. I'll proceed, but I'm happy to field questions at this point.
All right, thank you, Hal, for the first half of the lecture. If participants have questions, you can type them in the Q&A and we will moderate them. And if not, then we can leave time for questions at the end.
Please go ahead.
In the case of gravity, placing a bound on the number of states possible in the Hilbert space, I think there's something more going on than just the black hole formation, right? Is there something like entropy bounds, those things playing any role in that?
Yeah, so I think maybe the strongest indication of that in the literature is this work of Bekenstein's, where Bekenstein was trying to understand what's the maximal information content that a region of space-time can have. And the idea is that this bound really does bound the information content. And you can track that as a number of states. But the trouble that we all have in quantum gravity is that we don't yet have a detailed understanding of what those microstates are. Nonetheless, what the claim I was making is that this bound seems to be robust to the exact identification of what those microstates are. So yes, we want to understand what they are. Yes, we want to pin it down, but it doesn't matter from the side of this bound. We keep encountering this bound no matter how you formulate the microstates.
Got it. Thank you.
So there's a question that's come up in the chat. How do we know that a consistent theory of quantum gravity will necessarily resolve singularities? Also, why do we need to resolve singularities? Is there an a priori reason we want a theory without singularities? So, no, there's no claim that quantum gravity necessarily resolves singularities. That's when we add the necessarily in there, we're asking for a mathematical theorem. And today, the spirit of my argumentation is not of mathematical theorems. As I said, there's no example I know in physics, and please tell me if you know of one, where a theory predicts infinity and we believe that's the correct answer for the prediction. So we're kind of going the other way around here. We're saying that general relativity predicts infinite density on the interior of a black hole. And we don't think that could be right. Now, is it certain that quantum mechanics is going to resolve that? No. But it's quite reasonable that quantum mechanics could resolve that. The analogy that I like a lot for this is to think about the hydrogen atom. So in the hydrogen atom, you have an electron orbiting the nucleus, and the electric field should be allowed to carry away radiative energy. And so you suddenly run into this mystery. How is it that the hydrogen atom is stable? You know, the electron is orbiting, that orbit is necessarily accelerated. Acceleration causes electromagnetic radiation. Why doesn't the electron just cycle down into the nucleus and crash into the nucleus? Well, quantum mechanics stops it from doing that. In the quantum mechanical theory, there are only certain allowed orbitals. You can't have an orbital that is closer to the nucleus than the ground state of the hydrogen atom. So somehow you can, if you wanted to think in a intuitive classical way, it's like quantum mechanics provides a pressure that forces the electron away from crashing into the nucleus. So I think one of the intuitions behind quantum mechanics resolving the central singularity is that it's quite possible that there's just um, no way in which you can condense matter into a smaller region than some size, say the Planck area. And as such, you can't get infinite density. We can't get more and more mass accumulated into a smaller and smaller region because we've cut off how big the region we can consider is. So this is the intuition behind why quantum gravity might resolve a central singularity, but I know of no result that proves that it will. Your second part of your question is, do we need to resolve singularities? In the short term, no. You know, black holes are causally isolated from us for exactly the reason that we said that they're generic, right? We said that the black hole, the collapsing matter forms a trapping surface, and this trapping surface causally separates the interior of the black hole from the exterior. So we're just causally separated from the central singularity, and we have no concerns. But it's somehow the drawing together of the different pieces that makes us think, ooh, this might be important. So black holes can Hawking evaporate, as we were just discussing, and so maybe that eventually would expose a central singularity. And there you really run into a question of, like, what does that mean? What is physics telling us if we have this infinite density at the center that we can suddenly now see, we could probe? That would be very strange. So, so that motivates us to try to better understand what it is that the theory could do, we as theorists could do to change our theories to get rid of this concerning possibility. All right. Second question in the chat: is there an issue? With higher mode virtual particles creating virtual black holes? It seems like there would be an interaction which then prevents higher modes from excitation. So that's a really interesting question. I'm gonna respond to part of your question and skirt the rest of it for another time. The part I'm gonna respond to is something that I meant to say before and haven't gotten around to. There are things about both Hawking radiation and this Unruh-Davies Fulling effect that I'm not satisfied with my understanding of. So I think we should continue to develop these techniques and understand them more in detail. So let me give an example of this. And it's related to your virtual particles. People sometimes describe the Hawking radiation as we have a black hole. Outside the black hole, we have pair creation. So two virtual particles pop into existence. Of course, that pair creation violates energy conditions. One of the particles has positive energy, the other has negative energy effectively. You can only do this for a short time, and that's why virtual particles tend to come in and out of existence quickly. But the description that people sometimes give of Hawking radiation is that the negative energy partner in this virtual pair tunnels inside the horizon. It's a beautiful calculation you can do to check that its negative energy outside the horizon becomes positive and hence a real particle on the inside. And so now we have two particles that can just really exist and separate from one another. And the partner that stays outside the black hole is what feeds the Hawking radiation. It's a lovely story. I think it's quite interesting, but it seems to have lots of problems. Somehow this virtual particle pair, it's not obvious what the scale of their, say, Compton wavelength should be. And the actual calculation of Hawking radiation doesn't describe this virtual pair. And it's much more likely that Hawking radiation, we know already that the energy scale is quite low, so it should be a long wavelength phenomena. Somehow Hawking radiation should have more to do with the effective potential of the black hole, backscattering within the effective potential of the black hole, than with near horizon effects. So, so I think there's a lot to understand in terms of virtual particles and a more definite, concrete understanding of Hawking radiation and how it proceeds. Jim Bardeen has done a lot of calculations of quantum field theory and curved background calculations around this, and is very compelling and interesting points on this front. So you're asking about virtual black holes. I understand. I'm going to leave that aside for now, but I'm happy to come back to it later. Another question, and maybe I'll take two more and then we'll move forward.
Maybe you can take one more from the Q&A, and then there's also a raised hand. And then
wonderful. I didn't see the raised hand. Sorry about that. How much confidence do we have that the region between the horizon and the singularity behaves as per general relativity? It's an excellent question. The brief answer that I'll give to that is that there's absolutely no indication that general relativity breaks down at the horizon. This is actually quite interesting. You and I could be falling into a black hole right now and have no idea. The way that that would happen is if the black hole was quite large, its curvature scale at its horizon is actually quite small and could even be less than the curvature scale that we experience here at the surface of the Earth. So we could be crossing into a black hole and not even know it. So it seems quite strange for quantum gravity or for general relativity, quantum gravity to kick in if that could be happening right now. Or another way of saying it is that it seems quite strange that quantum gravity would be relevant at low curvature scales. So my answer to your question would be that quantum gravity will start to be relevant as we reach the Planck density. So it's just taking those same h bar, g, and c basic units and figuring out what the energy density is that corresponds to them. And the Planck density is actually quite far into the interior of the black hole in, say, a Schwarzschild black hole. But your point is well taken, and I do think it's quite important. In this diagram on the left here, this Penrose diagram, I would say quantum gravity does not kick in only at the central singularity. It kicks in before that on the surface where the curvature scale becomes Planckian. So that's in terms of the area, 1 over the Planck area squared, or the Planck density, the energy density becomes Planckian. Same scale there. All right, there was a raised hand.
Yes, Ashwin, could you unmute yourself?
Hi, can you hear me?
Yes.
You can.
Yeah. Talk has been going well so far. Uh, and my question is, as we have seen so far, that the loop quantum gravity shows background independence, but how does it fit in the context of causality when some argue that quantum gravity would exhibit infinite causal structures?
That's a lovely question. So that's one of the points I'm going to make in the second half of the talk, is that causal structure should become dynamical and in a quantum theory of gravity. And dynamical causal structure means that that lots of things that we're used to assuming are just not going to work. We have to be much more careful, and we have to come up with some way of describing them that sort of doesn't presuppose a background causal structure. I'm gonna leave it at that for now, just because I'm gonna be addressing this so much as we go forward. But I understand, again, I haven't fully answered your question, but if you don't mind, to bring it back when we get there, or towards the end of the talk today.
Okay, that's fine. Thank you.
Yes. Johanna, I think I'll move forward.
Yes,
And
I think it's good. We can leave the remaining questions for later.
okay, great. And then I'll stop in time for more at the end.
Perfect.
All right. So I've tried to give you lots of motivation. I think, day one, it's all motivation. So I hope that you see that there's a physical need to quantize gravity. And I hope that as you move through this basics of quantum gravity series, that you come back to those 5 questions and you ask, how is string theory addressing this? How is asymptotic freedom addressing this? How is causal dynamical triangulations addressing this? In all the approaches, we want to start to situate ourselves with regard to the physical questions. And so I think those 5 questions we just went through would be a really good way to kind of keep coming back to and asking. So what does quantum gravity theory say about singularities? How does it address the fact that it's not a quantum field theory? How does it address the fact that localization is no longer possible down to arbitrary scales? How do we deal with matter content? And how do we deal with black hole evaporation? Those 5 questions, I think, are worth returning to again and again. But as I mentioned in the introduction, I want to give you some of the reasons that quantum gravity is difficult. Here I'm starting to steal pretty substantially from a wonderful series of lectures given by Simone Speziale. If you just search the web for Simone Speziale Introduction to Loop Quantum Gravity, you'll immediately come across some video lectures that he gave a few months ago. I wanted to mention them explicitly, partly because he does 10 hour-and-a-half lectures. I'm only going to be able to go into so much depth. And if you want more depth, if you want more technical treatment of some of the things I'm saying, Simone's lectures are an excellent place to pick that up. I think it's probably web browser dependent, but when I found them, I couldn't view them on the web. I had to actually download them and then view them that way. But they're an excellent resource. All right. So the first answer is the answer that you all know and have suffered and thought about and complained to your friends about, which is that we just have so few experiments to guide us in quantum gravity. You and me, at roughly 1.5 to 2 meters in height, are closer to the size of the observable universe than we are to the Planck scale. The observable universe, as we know it at the moment, is 10 to the 26 meters. The Planck length is 10 to the minus 35 meters. So we're actually much closer to the size that we would need to be to understand the whole observable universe than we are to the Planck scale. So that's to indicate that it's a hard problem to probe quantum gravity experimentally. In the Large Hadron Collider, the LHC, the energy scales we're reaching are enough to create the Higgs boson, a wonderful discovery of the last 10 years. And the Compton wavelength of the Higgs boson is 10 to the minus 17 meters. So our most powerful current particle accelerator is still 18 orders of magnitude away from the Planck scale. So this is a really tough challenge to directly measure quantum gravity. I don't mean this to be depressing. I think actually quantum mechanics and its discovery in the context or its development in the context of black body radiation, that context is partly because thermal physics is a statistical environment, or statistical mechanics is relevant for that problem. And statistical mechanics has a wonderful way of sort of amplifying effects. So, you know, if you were to say, Hal, you can't do anything but look for experimental tests of quantum gravity, I think what I would do is really try to understand general relativistic thermodynamics and statistical mechanics and look for quantum gravity effects in that context. But it's hard. And there are many problems with not having experiments. One of the biggest ones is that it can be really difficult to sort out what we should take as a key principle in a theory and what we should worry is wishful thinking. In the lectures I was just mentioning, Simone has a wonderful analogy. Simone says, it's like there's no adult in the room. The kids are fighting and there's just no adult around, nobody to arbitrate the fight. And you can see this sometimes, unfortunately, in research battles where the fight is not really a fight where we can resolve the issue. We don't know. We don't have the empirical evidence to sort out which way is correct. We're looking. It's an active pursuit, but without experiments, that's a struggle. That's the downside of this. The upside is the one I just mentioned, the advent of gravitational wave observations, some beautiful experiments that are looking for entanglement in gravitational systems. You know, there's a lot that I think is developing and exciting here, and I'll talk about that more in the future. Okay, second reason that quantum gravity is hard. I already told you that I don't think quantum gravity is a quantum field theory, but I want to try to put a finer point on this and tell you that there are profound conceptual differences from quantum field theory. These conceptual differences are part of what makes me hesitant to really take a quantum field theory approach to quantum gravity. So the first one is that in general relativity, there's no universal notion of energy or of time. You've probably heard this a fair bit, but I want to try and say it in a concrete way. Suppose there were a tensorial description of gravitational energy. I'll call it T, sort of to make you think of the stress energy tensor. And I've put two indices here, but I'm actually, it can be any tensor. I don't mind. I'm just trying to make it concrete. So here's my gravitational description of energy. Well, what's the whole point of tensors? I mean, not the whole point, but one important aspect of tensors is that they transform in a way that we understand. So this tensor expressed in a primed coordinate system is related to the tensor in the unprimed coordinate system by the Jacobian factors that you're used to. But we know a key part of general relativity is the equivalence principle, which is the fact that at any point in space-time, I can adopt coordinates, I can go to a reference frame in which there are no gravitational effects. This is Einstein's elevator thought experiment, right? If I'm in an elevator, I have no way of knowing whether it's an accelerated reference frame moving up or a gravitational field down. And more concretely, mathematically, these are just Riemann normal coordinates, right? We use a local coordinate transformation to bring the metric to the Minkowski form at the point that we're at. But if we've eliminated all the gravitational effects via this coordinate transformation, that means in this special frame that I've just described, the gravitational stress energy tensor is 0. But it's a tensor. So once I've found one coordinate system in which it's exactly 0, well, then by this coordinate transformation rule that we've just identified, it's always 0. So this is the problem with a tensorial description of gravitational energy. This problem is tied up with a lot of different features of general relativity, all of which are super fascinating. You can think about it as Noether's theorem. And Noether's theorem in classical mechanics gives you the conserved energy if you have time translation invariance, right? But one way of saying what we have here is a problem is if there's no energy, there's no unique notion of time. There's no unique way of saying we have invariance under transformations or translations in that time. So in fact, Emmy Noether discovered her theorem in the context of trying to sort out energy in general relativity. That's often lost, but she was in close contact with Hilbert, who was at the same time as Einstein trying to work out the action principle for general relativity. And Hilbert and Einstein were both confused about the role of energy, and they posed that problem to her. And it was working through that problem that she discovered this beautiful theorem that for me is the most beautiful theorem in mathematical physics. So no matter how you slice it, there's a problem of energy here. So this is a big difference from quantum field theory. When we work on a Minkowski background and we say clearly we know what we mean by the energy of a particle and things like that, that's a much, much more subtle issue in general relativity. Okay, so that's number 2. Sorry, that's just the first part of why we're very different from quantum field theory. The second part is that the vacuum state is no longer globally defined and doesn't generally have a nice symmetry associated with it. In quantum field theory, as I mentioned earlier, we have the vacuum state, which is Poincare invariant. So we can find a representation of a Poincare transformation, and the vacuum state is invariant under that transformation. That's just not available to us in a curved space-time. What notion of vacuum should I use? Well, even if I find one, is it only true in this vicinity of space-time? Is it true over here as well? When I don't have a symmetry to move that state around, it's not obvious how to consistently pick it for all observers. So this is a big problem. One of the ways we're going to talk about energy in quantum field theory and in general relativity is via local observers' measurements. But then that doesn't give us a global notion at all. All right, still different from quantum field theory. There's no fixed background causal structure. This is what one of the questions addressed, right? If we work on a background space-time and we study, particle evolution within that space-time, then we know the causal structure. We know the light cone structure. But if our theory is supposed to be a theory of the gravitational field, that we're trying to solve for the causal structure, we're trying to solve for the metric while we're doing the process of solving the theory. And that means we can't refer to some background causal structure to allow ourselves to do the calculations. Closely related to that, in quantum field theory, we often talk about microcausality. So if you have some observable O and you find the commutator of the observable at X and at Y and calculate the expectation value of that, microcausality is the statement that expectation value vanishes if X and Y are space-like separated. So I don't think I've set it up to this point, but I'm going to work in the metric signature minus plus plus plus. I do think it's the more natural one because Euclidean geometry, spatial geometry should have plus metric. So what do I mean by space-like separated? Well, I mean that the X minus Y inner product with itself is positive. So this whole setup fails in a curved space-time. We don't have a nice causal structure, as we were just saying. So it's hard to even talk about what we mean by space-like separated, so we can't even formulate this microcausality condition. So this is one of the reasons that not having a background causal structure is important. That's going to make it hard to say things like microcausality. All right. More of a mathematical point, less physical, but still interesting. The action of general relativity is non-polynomial in the basic metric variables. People will quite often tell you this and just assume you know exactly what they mean. And for years, I didn't have a clue what they meant. And so I thought I'd tell you explicitly what this means. So here's what non-polynomiality is about. In quantum field theory, we typically would compute something in perturbation theory. And the way we do that is we expand around a quadratic kinetic term. The quadratic piece is important because we want to be able to do a Gaussian integral. Even in a field theoretic integral, it's Gaussian integrals that we can do well. So here's a partition function z of some current j. And I'm going to illustrate it first with some scalar field theory. So here's my path integral. It's the exponential of an action and a source, say. What's the structure of that action? Well, it's this kinetic term I was just mentioning, S0, plus the interaction terms of the field theory. So in scalar phi cubed theory, we would have the standard kinetic term, the mass term, and say an interaction that's cubic. This is what makes it phi cubed theory. And the thing to notice about this phi cubed theory is that there's two pieces. The kinetic term is quadratic. That's the first piece. So that's why I called it S0 and separated it out. And the interaction terms are polynomial in the field variable. And just in the straightforward mathematical sense, phi squared and phi cubed. So how is it that we then proceed with perturbation theory? Well, we think of the Gaussian integral that is this first part, and then what we do is we take the interaction term and we think of it as being generated by functional derivatives with respect to j. We can pull down the phi's by doing these functional derivatives. So if we replace this phi cubed by that functional derivative, you can order by order generate all the interactions of the theory. So that's how standard quantum field theory proceeds. The Einstein-Hilbert action is different. At least in our usual metric variables, it's a different story. So here it is written out. R is the Ricci scalar. Lambda, I'm sorry, I used it in a different way in the previous slide. In the previous slide, I was thinking of a Lorentz transformation. Here, lambda is the cosmological constant. The G with no decoration is the determinant of the metric. And so this is the square root of minus the determinant of the metric. The minus sign compensates the minus sign of our signature, so that this is a positive quantity. And kappa is the same kappa that I introduced above when I was discussing Bronstein. It's the 8 pi g factor. This action doesn't depend on the metric variables in a polynomial fashion. It can't be written out like this. And the reason is twofold. On the one hand, there's this determinant of the metric under a square root. So this square root is messing up the polynomiality. So that's half the story. The other half of the story is that inside this Ricci scalar, you'll find that the inverse metric appears. And the inverse metric, well, that involves 1 over the determinant, right? And so you now have inverse powers of your variables as well as polynomial. So this is actually quite painful to think about as a perturbation theory in this form. I am going to hold back from talking too much about perturbation theory today, partly because you have John Donahue giving a series of lectures starting tomorrow. And Donahue is the leading expert on perturbation effective field theory approaches to gravity. So you'll get much more from John around these things. But I did want to point out this piece that in the metric variables, this action is quite inconvenient. All right, so I've given you this long list of reasons why quantum gravity is hard. I've just completed telling you that the action's non-polynomial. And another thing that I hope that John will take you through with more care than I have time for right now, you can study quantum gravity perturbatively. You take the metric and you break it up into the Minkowski metric plus a perturbation, or whatever background you want to work with, plus a perturbation, and you study the quantum field theory of that perturbation. As long as the perturbation is small, it's easier to control what's going on. But even in that context, it turns out that perturbative quantum gravity is not renormalizable. And this makes quantum gravity difficult again. I'm not going to go further into that one because I think you'll hear much more about it, but we can discuss it more as we go along. All right, so where are we? I've given you two reasons quantum gravity is hard. The first is that we don't have enough experiments. The second is that there are profound conceptual differences with quantum field theory, and I've listed out all those differences. But I have more reasons for you. And this is related to one of the questions that was asked earlier. There are substantial mathematical and technical challenges. Just at the math level, there are challenges to quantum gravity. One of these is you might want to give a characterization of quantum gravity a bit like our characterization of quantum field theory. When we go from quantum mechanics to quantum field theory, what people often say as an intuition is, well, in quantum mechanics, the number of particles you're studying doesn't change, right? We just have the particle content we started our model with, and that just evolves in time, and we study that particle content. In quantum field theory, what can happen is the particle content can change. We can have creation and annihilation of particles and things like that. And it's a nice description of what quantum field theory is doing for you. It's allowing you processes where the number of particles changes. So you might like to say something similar in quantum gravity. That is that quantum gravity is a theory where, for example, the topology of space-time can change. There are two nice examples of this that come up quite often in the gravitational literature. There's the so-called Hartle-Hawking no-boundary state. This is a beautiful idea that maybe the universe began from nothing. That is, it's like a particle creation of space-time. So to do this in practice, what you need is a topology change. You need to go from an initially sort of spherical space-time that has a beginning point at tau equals 0 and evolves Euclidean for a little while. Then you find a way to glue a Lorentzian metric onto that Euclidean metric. That's the metrical change that happens in this process. And then your Lorentzian cosmology evolves from there. That's the idea of the Hartle-Hawking no boundary. Even if you're not interested in something as ambitious as describing the birth of the universe from nothing, even if you just want to describe a process where the topology of your spatial manifold can change, something like this diagram on the right here, say I am imagining time going upwards and I have a single dimension that is a circle that is my space. That circle evolves in time, but I might want to imagine that that space can break up into two pieces. So the single circle can pinch off and break into two pieces, which are the evolution after there. That would be like a pair creation process of space-time. Obviously here I'm doing it in lower dimensions. Well, there's a good reason I'm doing it in lower dimensions. In lower dimensions, we have good control mathematically over the kinds of topologies that are possible. In 4 dimensions, topologies aren't even classified. We don't even have a good mathematical dictionary for all the possible topologies. So this is just a brute force, tough mathematical question that we don't know the answer to. And it's hard for you to do something like a sum over topologies that you might want to do in a string theory for 4-dimensional manifolds. Nobody knows how to control that sum. We don't even know how to describe all the topologies. Similarly, there are issues with the smoothness. The diffeomorphisms is a huge group, and the smooth structure on a manifold also has problems of classification. So there's just some tough math questions that are hidden behind some of the things we'd like to be able to do in quantum gravity. All right. So I'm not going to do it right now because I want to give you a little bit of a taste of what loop quantum gravity is about. But I do want to come back to the experiments that are open, and I'll probably save that for the last lecture in the series. But there are some promising experimental things to look into, and I want to bookmark that for you. I don't want to leave it aside. It's an important point. All right. So I've told you that we need quantum gravity. I've told you it's really hard. And so now I want to try and tell you a little bit about what the loop approach to quantum gravity is. As I said, I'm going to keep this rather brief today, but just to try to give you a teaser for what I want to tell you next week. A few features of the loop approach. All right, I have a kind of naive point I want to make. It's naive, but I think it's really quite interesting. It's that gravitational actions are naturally areas. I mean areas like spatial area that you're used to. The first indication of this comes all the way back from Kepler. Kepler was studying the two-body problem, the orbit of a planet around the sun, and understood that the conservation of angular momentum means that this planet sweeps out equal areas in equal times. Why is that? Why is area and angular momentum, why are these two things being connected by gravity? What's that connection? Well, the naive answer is just the dimensional analysis that I've been doing for you a couple times today and that we've seen, but I think it's really important. The integrand of any gravitational path integral is going to be the usual integrand of quantum mechanics, e to the I action over h bar. These classification problems mean we don't know how to do the sum over the metrics. We don't even know how to classify all the metrics, but it should have a structure like this. And that's because the exponent has to be dimensionless. This must be an action over an action. Well, we know the Einstein-Hilbert action, so we can at least look at this from that dimensional standpoint and put h bar in and see what do we get. I plug in the h bar to that action we were just looking at, and I expand what kappa is just so you can look at it. And lo and behold, you see that exact same thing that we've seen several times appearing. Here we have a c to the fourth instead of a c cubed, but that's related to the metric factor over here. And really the dimensional part is the c cubed. So we see the Planck area cropping up once again in the denominator of this action. But that means that dimensionally speaking, if I group the h bar with the other dimensions in the problem, the action is measuring areas. It's area over area. That's one way of thinking about where the Hawking entropy comes from. So this is somehow, I think, telling us very basically, very naively, that areas should play a key role in quantum gravity. And notice that I, unlike many people in the literature, I'm not taking a square root. I understand why people do that. They take a square root because then you get a length scale, and we're used to talking about length scales. But taking a square root is not an analytic process. That is, if you think about complex analysis and you take a square root, you introduce a singularity when you do that. And so I want to avoid taking that square root. The fundamental unit that's showing up here is the Planck area, not the Planck length. I mean, you could think of it the Planck length squared, but that's a weird thing to do. It's the Planck area. So let's take that seriously. So this leads to my first feature of loop gravity, and I'm just trying to motivate it for you, and we'll talk about it much more in the next lecture. But in 1986, the advent of loop gravity was partly that Abai Ashtekar discovered a set of new variables that describe general relativity. And somehow you know this from much experience in solving all kinds of Lagrangian problems. If you find the right set of variables to do a problem, the problem becomes much easier. And so these variables that Ashtekar introduced, one of them is the so-called Ashtekar electric field. The reason it's called electric is just by analogy with electromagnetism. You want to think of it as the gravitational field. And I'll tell you much more about how it describes gravity soon. But because of this analogy with electromagnetism, people call it the Ashtekar electric field. So what is this field? It's written EIA of x. Technically, the mathematical answer to what it is that it's an inverse densitized spatial triad. Oof, it's a lot of words there that I need to explain what it is. Triad very roughly is an orthonormal frame that you can use on a spatial slice. And then we'll talk about the inverse and densitized next time. But it carries these two indices, I and A. A you should think of as a spatial index. It's like the space part of the mu that we've been using throughout, the Greek index that labels the space-time coordinates. A is like a spatial part of that. I is what we call an internal index. And the reason that it's there is that this electric field is Lie algebra valued. Again, the analogy with electromagnetism is useful here. This is a Lie algebra valued field. So it's starting to indicate that we can think of gravity as a gauge theory. And that's one of the reasons for the Ashtekar variables, is we're going to be interested in this as a gauge theory. In particular, the thing that is easy to build out of the electric field, I've written here, you take the spatial Levi-Civita symbol, the completely anti-symmetric symbol, and you contract the electric field with the spatial wedge product of two forms. And this is a natural two form that you can build out of this. This actually starts to give you a hint as to why we are interested in this variable. In metrical gravity, you know well, the first thing you learned was that you can use the metric to calculate the length of geodesics in spacetime, or length of any curve in spacetime. Here, I've taken the tangent, so I'm calling the curve gamma. I've taken the tangent vector to that curve with parameter tau. And then I'm contracting those tangent vectors using the metric. Here I've used Q instead of G for the spatial metric. That's because I'm talking about space right now. So this is just the usual formula you know for taking the inner product of two tangent vectors using the metric, and the square root gives you the length as you integrate over the curve. Very similarly, the point of the Ashtekar electric field is that it's the right thing, it's the right variable to use to compute areas. We just said that we could make a two form out of it. If we contract the Lie algebra index, that is, we find the magnitude of this Lie algebra vector, that magnitude is a two form. Once we take the square root, we integrate that two form over a surface area, sigma, and you get the area of that surface element. So somehow the metric most naturally allows you to compute lengths. The Ashtekar electric field most naturally allows you to compute areas. And partly motivated by this dimensional analysis I was just taking you through, this is one of the reasons I'm really interested in this variable. It's kind of naturally computing the actions of general relativity, the areas of general relativity. All right. I also mentioned that it's giving you a gauge theory. The canonically conjugate variable to the electric field is an SU2 valued, so a Lie algebra valued connection. So you could think of the potential, the electromagnetic potential as the analogy here, and you can see that's where the notation comes from. This Ashtekar connection is like the potential for the electric field. And it's a connection one form on the spatial three manifold. And in particular, what I mean by canonical conjugate is that in the classical theory, you have a Poisson bracket. And the Poisson bracket of the connection with the electric field gives you a delta function. So these are the conjugate variables of the classical theory. These gauge fields have, so this is interesting and exciting because you're starting to write gravity in terms of a gauge theory. And that means it's coming much closer to the theories that we know in the rest of physics, electromagnetism, the strong and weak nuclear forces, all of them, we understand them as gauge theories. In particular, we know best how to quantize them as gauge theories. So it's exciting to be able to recast general relativity as a gauge theory. Here we're casting it as an SU2 gauge theory. And it really is just like SU2 Yang-Mills theory in that sense, except that we have an additional huge gauge that we don't have in Yang-Mills theory. That huge gauge is the diffeomorphism symmetry of the theory. And you can think of it as a gauge. It's just choice of coordinates, right? That's how we think of it. So that's not really changing the predictions of my theory. But the one of the main technical subtleties in treating general relativity as a gauge theory is going to be dealing with this diffeomorphism gauge as well. So that's the main complicating factor. We've brought gravity closer to the other gauge theories, but we've also enriched the gauge group. All right. I'm almost done for today. I'll take another round of questions, but I want to give you one more example. Again, partly because you're going to be thinking about perturbation theory, effective field theory, its renormalization with John Donahue. This is an example that's taken from Ashtakar's book, the book that came out soon after he found the new variables. There was a great deal of excitement in the community, and a lot of work was produced quickly in trying to understand the quantization of gravity using these new variables. So he poses a question that I find really interesting. The question is, are there features of classical general relativity that would indicate that non-perturbative quantum gravity is very different from perturbative quantum gravity? And it's just a toy example that he gives, but I think the toy example is really interesting because it points out to you that, oh, there can be a difference. And maybe perturbation theory could be harder than a non-perturbative approach in some instances. So what is this example? The idea is to consider a uniform mass density at a radius epsilon, so that it's a little spherical shell that carries a charge E. And I want to calculate the mass, but in the general relativistic sense, the mass energy of this shell of charge and mass. So if we ignore gravity, well, it's just however much mass we put down, plus the non-dimensionalized, that is, I set some constants equal to 1, energy of the self-energy of the electric charge. So the total mass is just m0 plus e squared over the radius of the sphere. If we turn on gravity, but we only turn on a Newtonian self-interaction, well, the Newtonian self-interaction is going to, much like the electric self-interaction, it's going to go like the mass that we put down squared. The only difference is that you get 2 factors of epsilon. So in a Newtonian theory, this would be your mass as a function of radius. And the surprising, interesting, important fact that's a limitation in all sorts of areas of physics is that this diverges as epsilon goes to 0. So true point particles can't really exist. They have divergent energy. So this is maybe a better way of answering one of the questions that was mentioned earlier. Why is a singularity a bad thing? Well, if we're going to reach all kinds of divergences if we allow for this kind of thing, if we have point particles with divergent energy. But what I think is interesting here actually is to modify this argument and include general relativity. So instead of just allowing the Newtonian self-interaction, in general relativity, it's all forms of energy that gravitate, not just mass. And all forms of energy gravitating means that the self-energy should be expressed in terms of the total m of epsilon, not just the mass that I put down, the bare mass. And so we get a quadratic equation for this self-energy. It's got m of e on both sides, but it's a quadratic equation. You can solve it. So you solve it, and this is the answer. You find m of epsilon as a function of all the constants in the problem. And what's intriguing here, this non-perturbative solution that we found to this toy problem, this non-perturbative solution is finite as epsilon goes to 0. You see it? As epsilon goes to 0, these terms die off, and we just get this contribution here, and it's finite. So this is a well-behaved theory now with a good point particle because of general relativity. But what's so interesting about this toy example is that we can also treat it perturbatively. So let's do that. Let's imagine that we're thinking of the weak gravitational limit. So we'll think of our parameter as being Newton's constant, big G, and think of that as being a small number. Well, then I want to take this complicated non-perturbative solution and expand it in powers of G to control my corrections order by order in the coupling constant, in the Newton constant. So I factor out one of the G's so that I've got that under control, and now I can do the Taylor series expansion of the square root. And you just write out all the orders of that Taylor series. And the fascinating thing is that every single term in this series is divergent. Right? Each one of these terms blows up as epsilon goes to 0. But we just saw a moment ago that the epsilon goes to 0 limit is perfectly well defined and finite. So it's in the perturbation, it's in the organization of the perturbation series that the divergence appears. So this is at least an indication that a non-perturbative approach could be interesting, could be yielding results that are different from the perturbative way of looking at it. I don't want to say that the perturbative results aren't interesting. I very much think they are. In fact, I mentioned to you earlier that I like to call semi-classical physics, the study of the small h bar regime of a theory. And there's a very exciting recent development in quantum field theory, which is called resurgence. And it's a very careful, high-order study of the small h bar limit of quantum field theories. And what they're learning in resurgence is that while this series is divergent, the way in which it diverges can tell you interesting things about the theory. So resurgence is well worth your time. It takes a bit to learn, but it's quite interesting, and I think it's a nice development that's current, and I would like to see people starting to put resurgence and quantum gravity together. All right.
Well, there's a raised hand. Maybe if it's directly related, we can allow for a question right now, but otherwise...
I'm gonna finish because I just have one more minute, and then I'm done for today, and we can do the questions.
Okay.
So I tried to tell you a few features of loop gravity. Those features were that there's a nice set of variables that makes the action polynomial. So it gets rid of that weird non-polynomiality that we saw in the metric. It's closely related to the units of the theory. It's expressed in terms of areas. It's a gauge theory, although it has a large diffeomorphism symmetry. But I think this makes this theory quite interesting. And it's a non-perturbative approach, and there may be real physics in that non-perturbative way of looking at things. So what's the rest of the course look like? This is just the one slide I have about this. Although there's an important change that I should apologize for right off the bat. The plan was to do the introductory lecture today and then do the rest of the 4 lectures over the next 2 weeks. That plan ran into problems in practice. I'm so sorry to make a change. It may be quite inconvenient for some of you, but I'd like instead to do once a week for each of the next 4 Wednesdays. So they're going to update the website with this information, but we're just going to do once a week. I think that's going to make it a little bit more possible for you to listen in on Donahue's lectures and this as well without being overwhelmed. That's my hope anyway. But sorry for the late change. So next week, next Wednesday, June 14th, I want to tell you more about this gauge theory that is gravity. I'm going to do that by trying to introduce you. We're going to start to get more technical, but I do want to introduce you to gauge theories. And a wonderful way to get introduced to gauge theories is by thinking about how cats fall. So the first part of next week will be the gauge theory that is a cat falling. Then I'll describe for you a little bit about continuum GR and how to write it in Ashtekar variables. And then I'll tie that back, those two things together in the description of the simplest quantum of space, a quantum tetrahedron, which turns out to be the cat falling problem in disguise. Turns out that quantum gravity actually is, when you cut it down to a finite degree of number of degrees of freedom, is just a falling cat problem. So that's a lot of fun. The week after that, I'll tell you about the main set of basis states that we use in quantum gravity. These are called spin networks. They were also introduced by Roger Penrose, and they help you to understand the quantum discreteness that comes from this loop approach to quantum gravity. One of the hardest problems in loop quantum gravity is to give a dynamical description of the gravitational field that to find how regions of space-time evolve. I'm going to introduce you in the third week, which is discussion 4 on this slide, to the spin foam approach, which is this discrete geometry path integral. And then the final week, Wednesday, July 5th, I'll try and tell you a little bit about the frontiers of loop quantum gravity, come back to this question of experiments, where we're trying to understand black holes better and open questions in the field. So that's the plan. Thank you all so much for your attention, and I'm happy to take your questions. I want to give a huge thanks to the Quantum Information Structure of Space-Time project and the Perimeter Institute for Theoretical Physics, both of whom have supported me during the time that I used to prep for this, this series. Thank you all.
Thank you, Hal, for the very nice introduction. We have a bunch of questions in the Q&A. Some of them you might have already addressed in the previous answers, but maybe we can go ahead. I think the last, yeah, so we can just continue with Kamal's question, maybe, if you want.
Okay, great. So Camille says, theoretically, we know there's a singularity, but what is the physical evidence that there's a singularity at the center of a black hole? Meaning there could be something else, right? Or nothing. Absolutely, Camille. As we mentioned already, this interior of a black hole is causally disconnected from its exterior. And so we have no causal experiment that we can do on the exterior that probes the interior structure. So we do not know that there's a central singularity. What the way to think about this instead is to say, what is my theory predict? And what I was describing for you today is that general relativity predicts that there's a central singularity. And it's that prediction that we don't believe. As physicists, we don't think that's reasonable. An infinite density at the center of the black hole, that doesn't make any sense. So we think that it's a limitation of our theory, not of nature. We hope that nature does something completely different, and we'd like to find two things. One is a theory that doesn't predict a central singularity, and we'd like to use that new theory to make predictions that we can probe. So ideally, we would use that new theory to predict, for example, something near horizon that we can measure with the Event Horizon Telescope. That would be ideal. Then we could maybe see the consequence of this theory on the exterior. So that's the goal. I don't think anyone believes that there really is a central singularity in nature. All right, Masi says, how do you know that in the center of a black hole there's a singularity. Couldn't it be that the mass collapses to a sphere smaller than the event horizon but bigger than a point? In that case, there would be no singularity, right? Yes, Masi, that's exactly right. That's the kind of thing we have in mind. If quantum gravity discretizes space-time at some level, even if it's in a subtle quantum mechanical way, then there may be a smallest grain of space, and the matter may only come down to that smallest grain of space, hence resolving this infinity, right? Even if we put a large mass, like a solar mass, in a Planck volume, that's still finite density. So that is exactly the kind of thing we're hoping a theory of quantum gravity will achieve, is cutting off this infinite density. Idris says the dimensionality of the Hilbert space for quantum gravity that you mentioned before, which Hal extracted from the entropy, does it give you an argument for the existence of quantum gravity, of a quantum of gravity, or instead the fact that gravity is just a hydrodynamical theory? Excellent question. I think that we are very much in the process of investigating that question. Hydrodynamical theories are extremely effective and excellent, but they still have an underlying atomic theory behind them, right? And so the question that we're trying to understand is that true for gravity as well? Is there an analog of a molecular or atomic theory of the fluid that actually helps us to understand what's going on better? You're right that it's sort of an orthogonal direction to the direction of the quantum mechanical piece. It may be that both things are at play. So one of the people that's worked the most and thought the most about this kind of interplay between these two questions is Laurent Friedel. And you could look into the works that he and Donnelly and Speranza, several people have done on trying to understand in what sense gravity, general relativity, is a fluid theory. So I think that would be an interesting set of connections for you. Ayush says, does the finite entropy of black holes suggest discrete spacetime structure at very small scales? What reasons do we have in favor of or against discrete spacetime as an ingredient of quantum gravity? Ayush, this is one of my favorite daily questions. I don't think I have a definitive answer for you. It's something I think about all the time. The thing that I think that it indicates is that the microstates are finite. So what those microstates are, whether they can be described as modes of a quantum field theory that have a generalized quantum field theory, or whether they can be described as a discreteness, is an open question. I'm biased towards and very interested in the idea that they might be a fundamental discreteness, a fundamental quantum mechanical discreteness of the geometry of space-time. So one of the things I'm going to describe for you in this quantum tetrahedron model is a dynamical model of a discrete geometry that has quantum geometric observables. That is, it has a finite spectrum for its areas and a finite spectrum for its volume. So that's one of the reasons I want to tell you about this quantum tetrahedron. I think it's a really nice model for a discrete geometry. And I think within loop quantum gravity, it's indicative that maybe there is that fundamental discreteness of space-time. But a discreteness of space-time immediately makes you worry about Lorentz invariance. And I think we have really interesting proposals for how to deal with that within loop quantum gravity, but I want to see more work there, and I want to see more concrete demonstrations that the discrete geometries we're working with satisfy that Lorentz invariance. So I don't want to make a definitive statement. I think it's an open question. I think it's a really interesting open question. Manuel says, are there any examples of other cases where the resurgence approach could be applied? Yes, it's a vast literature that that I really think is nice. One of the things I've been working on is trying to think about resurgence just in standard quantum mechanics, not only in quantum field theory, partly as a way to give a little bit more access to students to the subject. For the time being, I'll point you to Gerald Dunn, who is a researcher at University of Connecticut and has done a lot of work within resurgence, and I think has some of the nicest introductions to the ideas. There was a fantastic school on resurgence run at the Newton Institute about a year ago. I'll try and get at the link to that school so you guys could check it out. But that's got a really nice set of introductory lectures to resurgence as well. Javier is asking about ADS-CFT.
Maybe so there will be also a lecture series on ADS-CFT specifically. So I expect people to say much more about this. Maybe you can pick a few of the last questions. There was also a raised hand, and then we can slowly wrap up towards the end.
Okay, and Johanna, don't feel badly about cutting me off. We could go on forever. So maybe I'll do 2 more minutes and then
right.
We'll stop.
So you can pick the favorite one of the remaining ones in the Q&A and let the last raised hand go, and then I think we can safely close the session.
Okay, that sounds great, and I am happy we can do more questions in the future. Okay, Ansh is asking, isn't the perturbative and non-perturbative theories giving completely different answers a bit concerning? How can both be contradicting each other for the same system? Also, do we expect the theory of quantum gravity to solve the problem of definition of energy within GR? Okay, I might not tackle the last part of that because that's a big question, although there's really interesting work about that. So maybe I'll say a few things. Regarding the perturbative and non-perturbative giving different answers, actually, this is partly why I think resurgence is very interesting. There's something that doesn't always get emphasized when we learn perturbation theory and quantum field theory. Perturbation theory is not a standard Taylor series. It's not convergent in the way that a standard Taylor series is convergent. You know that as long as you're expanding in a small parameter for a Taylor series, the series converges. So you can just keep adding up the terms and eventually you'll get the total answer. Feynman diagrams and more generally semi-classical physics like the WKB approximation to the quantum mechanical wave function, these provide what are called asymptotic series. They're not convergent. If you kept summing the terms of a Feynman diagram, you would actually get infinity. Asymptotic series, you want to go to a certain order in the series and then stop adding more terms. There's a particular term within the series that once you truncate at that, you get the best approximation you're going to get for that expansion parameter. So they're technically divergent series. That sounds scary. It sounds like we're dealing with something that's not mathematically well defined, but it's not true. Poincaré and many since have given good definitions of what we mean by an asymptotic series and how we should use them. And resurgence is in some sense a codification of all of that into a physical framework where you can use it very practically. So, so no, it is not disturbing to me that the perturbative and the non-perturbative approaches give different answers. I wouldn't have expected the perturbative approach to give the right answer unless I analyzed it correctly, unless I did the analysis in a very careful way. And so that's part of what I'm trying to point out, is that perturbation theory is a little bit more subtle than you might have thought it was when you were first learning it. Regarding your second question about whether we expect quantum gravity to give us a good notion of energy in GR, this point caused a lot of confusion amongst researchers in the last 10, 20 years. And to address it, they've been thinking more and more about what it means to have a gauge theory where you have boundaries in the gauge theory. So, you can try to study space-time as a whole, that is globally study a whole space-time. But you could also try to cut out a finite region of space-time and just study that. But if you cut out a finite region, then that region has a boundary. And the gauge theory with a boundary has a subtle relationship with energy. And it actually helps a lot to understand what that relationship is. And I hope to get into this a little bit, but it's a big topic, and there's much ongoing work around it. I can, again, mention a couple of names so you can look up some of the work. Mark Geiler, Daniele Pranzetti, Laurent Friedel. Lots of people have been trying to think about gauge theories with boundaries. Simone Speziale, who I mentioned earlier, and clarify what kind of notion of energy we have in the context of a boundary. And we're hoping that both helps us better understand the classical gauge theories, but also their quantization. So I don't know if I think that quantum gravity is directly going to address that question, but it's certainly intertwined with better understanding of quantum gravity, trying to pull that question out. All right, I'll stop there for today.
Yes, thank you, Hal, very much. It's a pleasure to listen to you, and I'm really looking forward to the next lectures. So as you said, the next lecture will take place on Wednesday, next Wednesday, and then we'll continue each Wednesday with the loop quantum gravity lectures. Otherwise, tomorrow there starts the perturbative quantum gravity and effective field theory lecture by John Donoghue. So thank you for participating, and see you soon.
Thank you all. Thank you for the wonderful questions.
Bye.
Thank you, Hal.